Yeah, there it is. Okay, number 3, a little bit more to the point of this section. Finally, we're seeing an exponential, or sorry, a logarithmic graph. First time we've seen it. The graphs of y equals 10x and y equals log x are shown below. These should be now very familiar graphs to you, right? We know that a few things about these graphs. We know that the exponential graph has a horizontal asymptote at y equals 0. We know what this point is, right? What is this point? You can tell me. Yeah.
0, 1?
Yes, 0, 1. Good. We know that point is 0, 1. That's important because when we do our translations on the test, we need to know which point to move, right? And that's a key point on exponentials. And so likewise then, on our logarithmic graph, what is this point?
1, 0.
Yeah, good. 1, 0. Okay? And we know on our logarithmic graph, Daniel, what's our vertical asymptote?
Y equals 0.
No, that's a horizontal asymptote. Y equals 0, it looks like this, right? I'm talking about this blue. The blue function.
Yeah. Oh, x equals 0?
Right, x equals 0. It's tough to see because it's so small, but yeah. Okay, discuss how the instantaneous rate of change in the y values for each function changes as x gets larger. So, who can tell me on the red graph now, as the x value gets larger, what happens to the instantaneous rate of change? Alan.
It increases.
Right, it increases. So this tangent line that I'm going to draw gets steeper and steeper and steeper. Okay? And likewise on the logarithmic graph, Lyndon, what happens to the tangent line? Right, it flattens out or it becomes less and less. Okay? So that's really the only points we're looking at. Okay, and we see that here. They're drawing the tangent line there, and then they draw it here, and then likewise on the blue graph, they draw it there, and there, and then there. So the instantaneous rate of change in the y values is very large for small values of x. Small values of x, it's very large. As x gets larger, the instantaneous rate of change gets smaller. So as x is getting larger, the instantaneous rate of change gets smaller. Very quickly, as x approaches infinity, the instantaneous rate of change approaches 0. We're getting to it, a 0 line. All right, quick summary. The average rate of change is not constant for exponential and logarithmic functions. The instantaneous rate of change at a particular point can be estimated using the same strategies used with polynomial, rational, and trigonometric functions. What are those strategies? Kevin, right here.
Sorry, sir?
What are the strategies that we used to find instantaneous rate of change?
We could use what was it, difference quotient.
Right? And the other one? Involves a graph.
Secant line.
No.
Tangent line.
Yeah, it's the tangent line to the point, right? The slope of the tangent line, right? So slope of tangent line. Okay, the instantaneous rate of change for an exponential logarithmic function can be determined numerically or graphically. Okay, that's right here, numerically and graphically. The graph of an exponential logarithmic function can be used to determine the period during which the average rate of change is least or greatest. So that's just going across the graph, finding where it's the steepest is the greatest, where it's the least steep is the least. The graph of exponential logarithmic functions can be used to predict the greatest and least instantaneous rates of change when they occur. Same thing, same idea. Any questions?